Welcome to the optical communication course. Today we will learn a photodetector. So we have learned is earlier that is about a source. That source is about a light emitting diode, and that source generates that a light or it emits a photon. So that a source is we have learned that is a LED or a laser that we have learned. Now we have a optical fiber we say, and at the end we have a detector. When light falls on this detector, so then it will generate that a input current pulse. We have the input current pulse as the input to the source, light emitting diode and laser. So then current will be converted into a photon of energy, that is a light. The light launch inside the fiber, then it is propagating through the fiber. Then at the end we have a detector. So the role of a detector is what? That light will falls on the detector. Then detector convert that light energy into the electrical energy. So means that is a current. So we'll get that output in the form of a current pulse. Now we will learn here a photodetector. There are the two types of photodetector, that is a pin and a avalanche photodiode. P type material, N type material, and intrinsic material here. An avalanche photodetector, avalanche multiplication takes place in this particular detector. There. Since the length of the fiber is too large, so when your light is launched inside the fiber, that light is propagating throughout the fiber. If that length is large, so at this receiver, that intensity of this particular light is very low. So that intensity light is very low. So now our aim is here, means detector, role of a detector for a small light or a small intensity of a signal, light signal, that can be converted in form of a electrical energy. So means our detector here, so detector detect a very low level of a light. So now that's why we can that is about the detection of the signal. And for a given particular light, it has to produce a electrical signal. So that is nothing but a response. So how your system will respond, or we can say that a response of a detector here, or we can say that a sensitivity, because for the small values of a light falls on the detector, your detector should respond. So detector should sense whichever the light falling on this particular detector, and then it will convert into a electrical signal. So now what happened, because we say that length of the fiber is a large, so that's why automatically we can say that intensity of the signal will reduce here. So means we need a circuit, we need a detector, it will respond for the very low light there. So means performance of a detector, if we calculate or if you obtain, so we need to talk about the what will be the responsivity of the detector. So means for a given particular light, it will generate a current. So that is nothing but a responsivity of this particular detector there. Now this detector, it will work for some particular wavelength of a signal. So what will be the cutoff wavelength of this particular detector? That we will learn here. So cutoff wavelength is generally it is depending upon that what will be the material we are using and that energy gap of that particular material. So the detector will respond for the very low light. In addition to that, even if some noise is there, okay, even if that noise, or we can say that there is maybe a temperature variation in the detector, so detector should respond to only that whatever the current pulse there. Means at any condition, the detector is to be worked, even if any changes or variation in the temperature occur, your detector should work for the given variation, or your device will work for the lifelong there. So what will be the operating life of that detector? That we should know there. As I mentioned earlier, there are the two types of a detector, a pin detector and a avalanche photo detector there. Now we start here with a pin here, and now we will see that how that pin diode is constructed there. Now we say that a detector means what? Light falls on this, it will generate the electrical pulse or electrical energy. So how it will generate that electrical energy? So that's why we need to learn about how your source will generate the photon there. Because when current pulse applied to the diode, then whichever the electrons we have, they move from the high energy band to the low energy band. Means higher energy state to the lower energy state. Means recombination of electrons and holes take place. So they will move from the higher energy band to the lower energy band, or you can say that from conduction band to the valence band. So generally we have a source that is about LED. It has a valence band, and this one is about a conduction band. Now electrons will come from this conduction band to the valence band, so they give up their energy in the form of a photon, and that is equal to Eg, or that is equal to band gap of a energy there. Now that is about a working of a source. Now here electrons and holes recombine in this particular region, or at junction or a depletion region, and it will generate that photon of energy. Now the reverse will occur in the detector. So when a for the given particular material, it has a valence band and a conduction band right here. So when incident photon will fall on this laser diode or detector there, so what will happen? That flow of electron in that direction and hole in that direction. Means photon of that HV energy that will be absorbed inside this material, and then it will generate a electron hole pair, and that electron hole pair generation takes place inside the detector, and due to that it will generate the current. Now then, how this electron and hole pair generation takes place inside the detector, that we will learn. We will learn first a pin diode, because we say that because of that incident photon it will generate the electron and hole pair. But we say that here whichever the light falls on the detector, all the photon will not generate the electron and hole pair. So sometimes what happen in this detector there, so whichever the electron and hole pair generated, they may recombine. So when we say that electron hole pair recombine, means that is nothing but loss for the detector here. Means light will absorb here because that electron hole pair recombine. For this given diode, we apply the reverse connection, reverse bias, so that electrons and holes will attract at that particular metal contact, and because of that, that current will be flowing through this diode there. Now, as we say that for a source, that active region is a very small, Similarly, for the detector, again that active region means where that this reaction takes place means photon of energy fall on this. So that active region here in the detector, so it will be a very small. So if we are using a LED, so in that case, for the light emitting diode, that fiber has a large core size because it has a large spectral width. But if you consider that laser, it has a narrow beam, so narrow spectrum here. Okay. So in that case, that core of the fiber is small. Similarly, that small core size, this light emitting from that small core size, it is to be detected by this detector there. So that photo detectors or whatever the device we are using, that detector device, that detector is to be a very small in a size, and it has a high sensitivity of light, and it has a fast response time. We can say that it has a fast response time and it has a high sensitivity and it has a small size. Because that fiber, even if we say that fiber, any application of fiber, we say that fiber it may be of a small size. So we will see here how your pin diode work and what is the structure of this pin diode, that we will learn. Now we consider here for this pin diode structure, we say it has a P and N here, P type material and N type material, which it is just like a diode structure. It is a P and N region, and in between that P and N region, it has a lightly doped intrinsic region, that is about a I, which it is a N type lightly doped intrinsic region. And this one, we say that we will apply the reverse bias to this diode, so it will generate the light. Light will fall on this particular diode, it will generate the current there. So that is about a current. We say it is about a IP, and this is about a load resistor RL. Will get that current, output current here. And we say that when light falls on this, when the light falls on this, so then what happen? It will generate that electron and hole separation of a carrier takes place. So we have that electron and hole in this particular region, that intrinsic layer. So electron will move in this direction, hole will move in this direction there. Because of this metal contact, okay, if you see that negative, this one is negative supply here, negative, and this one is the positive. So holes will be attracted at this contact and electrons will attract at this particular contact. Now this is nothing but a reverse bias operation of this a diode there. And this intrinsic layer, or you can say that this layer is a depletion layer or a depletion region of the diode there. Now if you represent that a optical power level inside this pin diode there, So we have this for the given particular structure. We say this is about a P and N here. Here we have the optical power or the optical power decays exponentially. Here it looks like linear now. It is exponential. It will decay exponentially there. This is about a power level of this diode. This is about a zero. This one about W with respect to X. This we can say that a photon of a flux. We can say consider the photon flux or photon emits from this particular fiber. When photon falls on this detector, because it will propagating through the layer, and it will be reach to this intrinsic layer there. Suppose we consider that it has a power level of a Pin that will be falling on the detector at x is equal to 0, at x is equal to 0. Then what happen? The power level P of x at a distance x we just consider here. So we can calculate that a incremental power level because of that a flux is travel, and then we can say that input power we can have it is about a flux is travel through this, and so that's why we can calculate that a power in terms of a incremental power with a incremental distance. So incremental distance we say that is about a delta x here, and then because of that incremental change in the we say optical power we can write in terms of a dpx, and that will be depending upon that alpha s, and that is a lambda and a p of x. Now this alpha s is nothing but what? A photon absorption coefficient. Photon absorption coefficient, and it is depending upon the wavelength. So now if we integrate this equation, so we'll get that a p of x is equal to p in exponential of a minus alpha x alpha s. I will write here p of x is equal to p in to exponential of minus alpha s into x. Means, means whatever the photon of a flux, okay, we can say that it will travel through this particular diode. So means we can say that a light is falling. So that is about the input power level. It is propagating through the material. That is about the input power material that is propagating through the material, and the material is having the distance incremental distance is about a delta x here. So we can say that a power level we can calculate. This one is about the incident power level. So we can say because through the material it is propagating, so that's why incident power level will be decaying throughout the distance. This is about it. Through this material, your uh, input power level, and it will be decaying with respect to the distance there. That is about a P of x. We can calculate. That is absorption means what? Which it is nothing but a photon absorption inside this particular material or in this particular region there. Now, if you see that a power level it is depending upon that depth of penetration of this power level inside this intrinsic region. And we say that that intrinsic region has the width W. That's why it's 0 to W we say. So that's why that power is exponentially decaying. And then this I is a very high, large, okay. It is about a very large one. That P and N is a very small. But light propagating through this P layer, because this P layer is a very thin, okay, this P layer is very thin and propagating through this. So, but some particular photo carrier or some photon, they may be absorbed inside this particular P region. So that's why we can say that that is about the absorption coefficient because they are propagating through it. Now next, how your detector work? Because as we mentioned there, we have the photon of energy that will be propagating through it. Propagating through photon is propagating through the device. So then when it will be propagating through the device there, so then it will generate the electron and hole pair. And because of that generation of the electron and hole pair, this is about generation of electron hole pair. When your light falls on this, electron and hole pair generated. So that's why that current is propagating through the device. So here is a simple energy band diagram for this pin diode, and we say that this is about a band gap of energy, that is about the Eg for the P here. Okay, maybe small. We just say that this is about the intrinsic layer, and this one is about, you can say it is about the N, P, I, and N. This one is about a conduction band, and this one is about a valence band. Okay, otherwise you'll get confused. And we say that a photon of energy, that HV, is to be a greater than that Eg or equal to the Eg. Maybe a greater than or equal to the Eg. So when that photon of energy that will fall, so then it will generate that, you can say, a electron and a hole there. It will generate that electron and hole pair. So this is about a photo generated electron, and this one is about a photo generated hole. And this one is nothing but what we can say, a depletion region. This one is nothing but the depletion region. Now that photon hole is generated, that we say it is about the direction, it is moving in that, and electron will be moving in that direction. Okay, that's what we are saying. This direction of this photon hole is generated, that is towards P, towards N, and then it is about a connecting to the reverse bias there. And then whatever the photon of energy is there, according to that, number of electrons and holes are generated. These are nothing but a carrier generated in the depletion region, or we can say that a intrinsic region, that is about the I layer. In this I layer, it will generate that electron and hole. It will generate the electron and hole. Now again we say that there is a high electric field present in that particular depression region that causes the carriers to separate, and that will be collected at the reverse bias junction. And because of that, the electron will flow because of that electron hole pair generation. So that because that electron and hole pair they are moving, and because of that a current will flow through it, and that current is called as a photocurrent. And that photocurrent is depending upon that what will be the a number of charge carriers generated throughout this depletion region. So that's why we should know that how many number of holes and the electrons are generated, and they move a distance, and that distance is called as a diffusion length inside the depletion region. So that's why we can calculate that a time takes for an electron or a hole that will recombine, that particular time is called as a carrier lifetime. So we can calculate that a carrier lifetime for a electron there, that is a carrier lifetime for the electron and a carrier lifetime for hole. Okay, for electron, and this means for the hole. And that charge carrier move the distance ln, so that's why that length or a diffusion length that is related to the electrons ln is equal to whatever the distance traveled dn with respect to that the carrier lifetime, just 1 by 2. Similarly for the hole, lp is equal to the distance travel. Okay, and then we can calculate that whatever the tau p raised to 1 by 2 here. So that is about the distance travel, and we can calculate that from that means in that particular intrinsic layer. So diffusion of electrons and diffusion of hole. So that's why the diffusion coefficient for the electron and hole, that will gives us the whatever the distance traveled by this particular electrons and holes there. And we say that there will be absorption of this photon of energy. So that absorption is depending upon that what will be the wavelength we have. So means light is there, light falls. We say that EHV is equal to EG. That is depending upon that wavelength. So that's why whichever the material we are using, when the light falls in that particular material, so that material has some wavelength, and that wave material have some particular wavelength, and that wavelength is depending upon that band gap of energy, that is about the EG. So for the given material, there should be some upper cut of wavelength. So we can calculate that upper cut of wavelength for the given band gap of energy material, that is lambda c is equal to what? Hc by Eg. So it is equal to what? 1.24 by Eg, that is a electron volt. And this one is in terms of a micrometer there. Because that absorption coefficient or absorption is totally depending upon that what will be the material and what will be the wavelength there. So for a given particular material, what will be the absorption coefficient? So if you consider that with respect to the wavelength and all, this one is about a lambda, and that is about the absorption coefficient alpha. So for the given material, we say that zero point 0.4, zero point 0.6, 0.8, 1, 1.2, 1.4. So if supposed to be, if we are using a silicon, in that case that absorption coefficient will be a 1 here. So if you consider that germanium, that absorption coefficient will be likewise. For the different coefficient, different material, they have the different absorption coefficient, and that lambda, that wavelength, is depending upon the material itself. And we say that the cutoff wavelength is a 1.06 for silicon, that is 1.06 micrometer for silicon, and 1.6 micrometer for germanium. Now, why we require this cutoff wavelength? Because we say that when that photon will be incident inside the intrinsic material here, so it will generate the electron and hole pair. If that wavelength is a long, if wavelength is a long, so in that case for the given material, if that wavelength is a long, so in that case when light will be fall on this, so in that case that photon of energy is not sufficient to excite the electron and hole from the valence band to the conduction band. Because HV, that energy gap, is depending upon that wavelength, and if that material has a longer wavelength, so then it will not generate the electron on hole pair, or electron will not move to the conduction from the valence band to the conduction band. So then no current will be flowing through it. Okay. So that's why we should know that for a given material, what will be the cutoff wavelength. And if supposed to be there will be a lower values of this particular cutoff wavelength there, then we say that it's for the longer wavelength it did not work. Similarly, for the shorter wavelength, if that wavelength is shorter, so whatever the electron hole pairs are generated, they are very short. Okay, means we can say that whatever the recombination time required, that will be very short to generate that electron and hole pair, and that whatever the electron and hole pair generated there, they will be collected at the photodetector there. So, so in that case, if that is about a short wavelength, so it will be collected at this particular surface there. So now we can calculate that whatever the total power absorbed inside this intrinsic layer with respect to W, because it is with power absorbed, it is depending upon the length. We say it is about a exponential variations. That's why we can consider that about a W here is equal to 0 to W absorption coefficient, whatever the P in, then exponential of minus alpha s into x to dx is equal to P in 1 minus e raised to minus alpha s to W. Now then we can calculate that whatever the photo current generated. So that photo current generated, it is depending upon that Q by HV into P in 1 minus e raised to minus alpha s W 1 minus RF. That RF is the reflectivity. This one is about a reflectivity, that will be for the given particular material, or we can say that is about the at the entrance of the pin diode. Okay, that is about the reflectivity. And we know that a Pin is about the incident power, a Q is about a electron charge, and HV is about the photon of energy there. So that is about a photocurrent and absorb power. So based on that, we can find out, because a photodetector will generate the electron and hole pair based on that incident photon. Okay. So according to that, we can calculate that a one important parameter of this photodetector, that is about the quantum efficiency and its response speed. So this quantum efficiency is depending upon that band gap of energy HV and operating wavelength. Quantum efficiency, it is depending upon that band gap of energy. Then it is again depending upon that operating wavelength, quantum efficiency and response time. Okay. Operating wavelength, and again it is depending upon that what is the doping and what is the thickness of this particular doping. Okay, band gap of energy, the operating wavelength, doping, and the thickness of this P, I, and N in this particular region there. So we can calculate that a quantum efficiency is nothing but what? A number of electron hole pair, we'll just write electron hole pairs generated per number of incident absorbed photon of energy. So we'll get that a quantum efficiency, that is nothing but what? Number of electron and hole pair generated. And if you write the equation, it is depending upon that IP by Q, that is number of hole pair generated, and incident power by HV. So here that IP is nothing but what? A photo current, and P in is about the incident power there. Means for a practical that diode, when the photon is incident in the diode, on the spin diode, so it will generate the electron and hole pair. So because of that generation of electron hole pair, it will generate the current. We'll get that current. So we should know that how many of a electron and hole pairs generated inside the particular photodiode. So generally it is that for a pin diode, so the efficiency, quantum efficiency is about a 30 to 95%. Means what? We can say that they will generate the electron and hole pair. If we have a 100 number of photons, they will generate a 30 photons. We say that efficiency, quantum efficiency is 95. So you can say that they will generate out of 100 photon of a light, they will generate that 95 electron and hole pair. So that's why a 95% efficiency. So now to get that higher quantum efficiency, so we should know that that depletion layer, that size is to be large, or you can say that it is to be a high, that is the thickness is a large there. If there is a thickness is a large, so that's why we, whatever the photon will be incident in that particular layer, so that will generate that electron and hole pair there. So it is totally depending upon that depletion layer. Quantum efficiency, it is depending upon that depletion layer. And a drip time, carrier drip time that will determine the response speed of the diode. So we can say that based on, we can find out the responsivity. That responsivity R is equal to IP by Pn, or can say that NQ by HV. That is about the responsivity. Now, if you see the responsivity here for the given material, because that responsivity it tell you what will be the photocurrent generated by applying the what will be the input power there. So that's why it is just like a function of a whatever the current, because input power we can say here, as well as it whatever the current is generated IP. And generally, if you write in terms of a quantum efficiency, a charge, and HV is nothing but what we can say H is Planck constant, V is nothing but a wavelength. So means responsivity is depending upon that wavelength there. So for a given particular material, if you draw a responsivity curve, so this one is about a responsivity, and this one is about the wavelength, zero point 0.7, 0.9, 1.1, 1.3, 1.5. So if you use a silicon material, responsivity is likewise. If you use a germanium, so responsivity is likewise. And if you use a indium gallium arsenide, so responsivity will be likewise. So responsivity for the silicon, for the germanium, gallium arsenide, and it is depending upon that wavelength there. And the photo that, again we can say that it is depending upon that efficiency. So the efficiency is supposed to be considered that 10% efficiency, 20%, 30, 50%, 30%, 50%. Likewise, this is about the efficiency curve. So means again photodiode efficiency, it is again depending upon that quantum efficiency, again depending upon that wavelength there, as the whatever the responsivity there. So that responsivity is nothing but what? It is a linear function of a optical power. That responsivity is nothing but a linear function of a optical power. So that's why we can say that whatever the photon current is generated, that is directly proportional to the P in here. Because current is generated based on this whatever the applied photon of a power or a incident power there. So that's why that responsivity, it will be a constant for the given particular wavelength there. So if you see here that equation of the quantum efficiency and this responsivity, then we can say that a quantum efficiency is not constant at all the wavelength. Okay, if you consider that it's not constant at all the wavelength, again it is not depending on, because we say that material, whichever the material we are using, according to that electron and hole pair is generated based on this whatever the incident photon is there. So we should know that for a given particular material, so what will be the incident wavelength, so that it will generate the photon of a energy there, or it will generate the number of electrons and hole pair. So that's why that responsivity and quantum efficiency, both are depending upon that material, and both are depending upon that what will be the cutoff wavelength. We say that a cutoff wavelength for the different material is a different here.